Part 5. Quantum Physics in Everyday Life. Quantum physics isn't just an abstract theory studied by scientists in laboratories. It's the foundation for many technologies we use every day, often without realizing it. The strange quantum world of particles existing in multiple states simultaneously, electrons tunneling through barriers, and energy existing only in discrete packets has been harnessed to create the modern technological landscape that surrounds us. Lasers, quantum light in action. Lasers are one of the most common quantum devices in our daily lives. Every time you scan a barcode at the grocery store, play a DVD, or use a laser pointer, you're using quantum physics. Lasers work because electrons in the laser material can only exist at specific quantum energy levels. When these electrons all jump down to lower energy levels at the same time, they produce the intense, focused beam of light we call a laser. The quantum principle behind lasers is called stimulated emission, first predicted by Einstein in 1917, when an electron in an excited state encounters a photon of exactly the right energy. It's stimulated to fall to a lower energy level, releasing another photon identical to the first. This creates a cascade effect where millions of electrons release perfectly synchronized photons, resulting in the coherent, monochromatic light that makes lasers so useful for everything from precision cutting in manufacturing to reading the microscopic pits on a Blu-ray disc. Transistors, the quantum foundation of the digital age. Transistors, the building blocks of all modern electronics, also rely on quantum physics. These tiny switches control the flow of electricity in everything from computers to smartphones to car engines. The way electrons move through the materials in transistors is governed by quantum mechanical principles, particularly the behavior of electrons in different energy bands. In a transistor, quantum mechanics determines how electrons can move through different materials like silicon. The concept of energy bands regions where electrons can exist comes directly from quantum theory. By carefully controlling the quantum properties of these materials through a process called doping, engineers can create switches that turn on and off billions of times per second. Modern computer processors contain billions of these quantum switches, all working together to perform the calculations that power our digital world. The quantum tunnel effect also plays a crucial role in some transistors. As transistors have become smaller and smaller, electrons can sometimes tunnel through barriers that classical physics says should be impossible to cross. While this can cause problems in some cases, engineers have learned to harness quantum tunneling to create new types of electronic devices. Medical marvels, MRI and quantum spin, MRI scanners in hospitals, use quantum physics to take detailed pictures inside your body. These machines work by manipulating the quantum spin of hydrogen atoms in your body, using powerful magnetic fields. The quantum behavior of these atoms allows doctors to create detailed images of your organs and tissues without surgery. Every hydrogen atom in your body acts like a tiny quantum magnet due to a property called spin. When placed in the strong magnetic field of an MRI machine, these atomic magnets align either with or against the field. Radio waves can then flip these atoms between different quantum states. As the atoms return to their original states, they emit radio signals that the MRI machine detects and uses to build up a detailed picture of the inside of your body. Solar energy, converting quantum light to electricity. Solar cells that convert sunlight into electricity are another quantum technology. When photons from the sun hit a solar cell, they give their energy to electrons in the material, causing them to jump to higher energy levels. This quantum process is what generates the electricity that powers solar panels on homes and businesses around the world. The photoelectric effect, which Einstein won the Nobel Prize for explaining, is the quantum phenomenon that makes solar cells possible. Each photon carries a specific amount of energy determined by quantum mechanics. When a photon with enough energy hits an electron in the solar cell material, it can knock that electron loose, creating an electric current. The efficiency of different solar cell materials depends on how well their quantum energy levels match the energy of photons in sunlight. The quantum future in your pocket. As we look to the future, quantum technologies are becoming even more integrated into our daily lives. Quantum dots in some TV screens create more vivid colors, Quantum encryption protects our online transactions, and quantum sensors in smartphones help with navigation and motion detection. The quantum world that once seemed impossibly strange has become the invisible foundation of our modern technological civilization, quietly working behind the scenes to power the devices and systems we depend on every day. Part 6. The weirdness of quantum physics. Quantum physics is strange because it doesn't match our everyday experience of the world. In our daily lives, objects are either here or there, never into places at once. Things happen for clear reasons, and we can predict what will happen next if we know all the details. A thrown baseball follows a predictable arc through the air. A dropped coin lands either heads or tails, and a cat is definitively either alive or dead. These experiences shape our intuitive understanding of reality as orderly, deterministic, and fundamentally logical. But in the quantum world, particles can genuinely be into places at once through superposition. Imagine an electron orbiting an atom's nucleus, unlike a planet orbiting the sun. This electron doesn't follow a single defined path. Instead, it exists in what physicists call a probability cloud, simultaneously occupying multiple positions until the moment we try to detect it. Only when we measure its location does it collapse into being found at one specific spot, as if our observation forces reality to make a choice from all its possible states. Quantum particles can also tunnel through barriers that should be impossible to cross. Picture trying to roll a ball up a hill in our everyday world. If the ball doesn't have enough energy to reach the top, it will simply roll back down. But quantum particles can mysteriously appear on the other side of energy barriers, without having enough energy to go over them. It's as if they temporarily borrow energy from the universe to slip through solid walls, a phenomenon that makes modern electronics possible, but defies everything we think we know about how objects should behave. Most strangely of all, the simple act of measuring or observing something can change what it is and how it behaves. This isn't because our measuring instruments are clumsy or disruptive. It's a fundamental feature of reality itself. In the famous double-slit experiment, individual particles of light or matter can behave like waves when no one is watching, creating interference patterns that suggest they somehow travel through multiple paths simultaneously. But the moment we set up detectors to see which path they actually take, they suddenly behave like discrete particles, taking only one path and destroying the wave-like interference pattern entirely. The weirdness goes even deeper. Particles that are far apart can affect each other instantly through entanglement, seemingly faster than light could travel between them. When two particles become entangled, measuring the properties of one immediately determines the properties of its partner, regardless of the distance separating them. Einstein famously called this spooky action at a distance because it appeared to violate his theory of relativity, which states that nothing can travel faster than light. Yet experiments have consistently shown that entangled particles can influence each other across vast distances instantaneously, challenging our basic understanding of space, time, and causality. This quantum interconnectedness suggests that the universe might be far more unified and interdependent than our everyday experience suggests. The boundaries between separate objects may be more of an illusion, created by our limited perspective than a fundamental truth about reality. Some physicists even propose that consciousness itself might play a role in collapsing quantum possibilities into definite outcomes, though this remains highly controversial and speculative. Despite how strange these phenomena seem, they have all been tested and proven in thousands of experiments over the past century. Scientists have observed superposition in everything from individual photons to surprisingly large molecules. They have measured quantum tunneling in semiconductor devices and radioactive decay. Researchers have demonstrated entanglement countless times, and even used it to develop new technologies, like quantum cryptography and the beginnings of quantum computers. The weirdness isn't a mistake, or a limitation of our understanding. It's how nature actually works at its most fundamental level. This reality forces us to abandon our comfortable assumptions about the world and embrace a universe that is for stranger, more mysterious, and more wonderful than our everyday experience could ever prepare us to imagine. The quantum realm reveals that at its deepest level, reality itself is probabilistic, interconnected, and fundamentally unknowable until the moment we choose to look. Thank you for watching this Part 5 and Part 6 explanation of quantum physics. If this video is knowledgeable and interesting, give us a comment and like. Also share with other like minds too. If you haven't watched the previous videos, the links of the videos are given in the below description. Do not forget to subscribe my channel. The next video, Part 7, the future of quantum physics and a conclusion.